No, I speak on behalf of the organizers of the Colloquio of Classe di Scienze o Scuola Normale, because they are all absent today for one reason or another, and Chiara asked me to introduce the speaker of today. And it's an honor and a pleasure to have here Professor Lee Roberts from Boston University. Now, you know that in physics, progress usually arrives on the press when you make a big discovery. It's good because people get attention. I mean, recently we saw on in putting together a telescope as big as the Earth in order to measure a black hole. Or 3 years ago, there was the Higgs boson arriving from LHC. But progress in physics is made also because there are people that can measure things with a precision that is absolutely fantastic. You know what is the weak interaction? Huh? The weak interaction is G Fermi gives a scale of the weak interaction. Huh? And Professor Roberts has been in the experiment measuring G Fermi with a precision of 0.5 per million. Huh? That is an amazing result. And in the last 25 years, Professor Roberts has been struggling on a topic that is also very close to Scuola Normale. He has been struggling in measuring the G-2 with an unbelievable precision. He will tell the details. But G-2 is close to Scuola Normale because G-2 was the battle horse of Emilio Picasso, that is has been our past director, and Emilio was central in doing the experiments at CERN on G-2, and also Lee will also, I'm sure, discuss about that. So, Lee, thank you.
Thank you very much. It's a pleasure and an honor to be back in the Scuola Normale. The last time I was here, Picasso was actually the director, and he had many questions, as he always did. So he was a terrific physicist and a great friend. Thank you. There we go. So what I'm going to do today is to tell you about experiments that have been going on for decades. And this is starting my third decade about today as a leader. And the experiment is called the muon G-2 experiment, so I have to explain what G and why it's -2 and all that. The instructions I received in my invitation said that they're held on Wednesday at 3, so we're ahead of time. And it's a unique opportunity for faculty visitors and so forth willing to address an audience containing biologists, chemists, mathematicians, and physicists. We understand that this is a lot of work. So I've been searching for any connection with biology, and I realized that all of the work I'm going to report on was done by Homo sapiens. So I'm going to answer some questions: what, why, who, and so what. So we have this standard model of particle physics, and it seems to explain everything we've measured. And people are trying in many different ways to find something beyond it. And since this is a broader audience, I thought I should briefly review the standard model and explain what and why it's interesting. So it turns out in the standard model they're a generation structure. And we're in the first generation, that is the atoms inside of us. They have electrons, and there's also a neutrino associated with it, a neutral particle, I think named by Pauli? No, Fermi. Okay. And then the second generation is called the muon, and as we sit here, 1 per square centimeter per minute is going through you from the cosmic rays. And then there's the tau which took many years to find and was found at SLAC. These guys interact. Our atoms are using the electromagnetic force that make atoms. And the weak force is governed by these two guys, plus this Higgs boson, which was found a few years ago. And that sort of completed the picture. And then there are three families of quarks. We're made of up and down quarks. And they interact strongly through the gluons. So there's the electromagnetic force, the weak force, and the strong force. And so I'm going to focus on this guy, which is really special, because its lifetime is 2.2 microseconds, which is practically forever on the subatomic scale, which permits very precise measurements of its property before it decays. And its mass is 207 times the mass of the electron, which gives it special sensitivity to physics beyond the standard model, all of which I will explain. So there are fundamental questions in particle physics. Why are we here? Why is there a antimatter asymmetry that allowed the early universe to end up as a matter universe? Why mass? Well, the Higgs. That's one thing we can check off. What's beyond the standard model? Well, there's a theory called supersymmetry that says for every particle we know about, there's a companion particle, and then one of my colleagues said, well, at least half the particles have been discovered. And what's dark matter and what's dark energy, because this standard model we know about is about 4%. And so I'm going to focus on an experiment trying to figure out what's beyond the standard model and searching for clues. So how do we find what's beyond the standard model? Good question. Well, the Large Hadron Collider has got the highest energy collisions and the chance to make the heaviest things possible there. And thus far, they found the Higgs, which is important, but expected. And we're waiting for something new. Precision frontier, you need a very intense beam, and then you measure something very, very precisely. And so you can make intense beams of neutrinos. The US is having a major program on that. And then intense beams of muons. We also have a program on that, but the Paul Scherrer Institute has also a very strong muon beam. And so what I'm going to tell you about is increasing the precision of the muon magnetic anomaly. And that, you will understand why, is interesting by the time I finish the talk. And in fact, I say here as a preface that the muon G-2 experiment has got the only tantalizing hint that there is something beyond the standard model. And I won't worry about what is it. The theorists worry about that. We're a large collaboration now. We have significant contributions from Italy. And a couple of my colleagues are here who played important roles. So let's go back. What is a muon? Well, it was first observed, the first published observation was in Zeitschrift für Physik in 1933 in a Wilson cloud chamber. They saw this track that was more heavily ionizing than electrons, and it was a particle of uncertain nature. There's the original German for you. And it was identified for sure by these two guys. And so what the heck is this thing? People were looking for the Yukawa meson, which carried the strong force, which is, we now know is the P.A.M, and that was much harder to discover, but this muon lived for a long time, and therefore it was found first. So, magnetic moment. There's an intrinsic magnetic moment that's associated with the spin of a charged particle. And this G factor has a value 2, and then an anomalous part, A, and so this quantity G-2/2 is the magnetic anomaly. And that turns out to be where the exciting physics is. So if you put a magnetic dipole in a magnetic field, there's a torque. And there's also an energy mu dot B. And this we teach our beginning students, right, in E and N. And for a spin particle, there's a torque, and you get the spin precession, Larmor precession. And, here's the vector diagram if you want to look at the. So here's the torque, and this is the direction the spin turns with this. I've made it a negative particle. And it's just like the gyroscope. In fact, if we knew gravity and we knew that precession frequency, we could calculate the moment of inertia. So here's the precision chart in particle physics. And of course, there was a lot of fanfare that the Z mass was measured to 20 parts per million. But already at CERN, a decade before, they'd measured G minus 2 to 7 parts per million. These two experiments I've been associated with. G Fermi was measured at Paul Scherrer Institute, and G minus 2 was measured at Brookhaven. It's half a part per million. Here's our goal, 140 parts per billion at Fermilab, and the electron G minus 2 is known much better. It all started with Stern and Gerlach, the measurement of magnetic moments. And so CERN published a paper, how to look for space quantization. And Gerlach knew how to make a very strong quadrupole field, because if you have a dipole in a field, the net force is 0. If you have a gradient field, then there's a net force on the dipole. And so you put this beam of silver atoms through this gradient field. Can you see that? I guess so. And so without a magnetic field, they got the one band, and with the magnetic field, they get two bands. And today, I don't know what you say here, but in the States, we say in our modern physics course, and that showed that spin was 1/2. And actually, they expected two bands from a relativistic theory by Sommerfeld. They were happy, and it took some number of years before it was understood what was going on. And in fact, in modern language, we understand that G factor of the silver atom, and thus for the electron, the unpaired electron, was 2. It was up to these two bold graduate students, Schmidt and Uhlenbeck, to put forward this idea of spin and actually get it published to explain the fine structure splitting in atomic spectra. And so what they said is that if you have a spin 1/2 particle and a nucleus going around it, there's a current, and so there's a magnetic moment interacting with this current. And the only problem was they got an answer that was too large by a factor of 2 for the fine structure splitting. And it was all sorted out by Thomas, another graduate student, who pointed out that you needed a correction from relativity, and then we call that Thomas precession now. And so many, many years later, Thomas wrote to Schmidt, I think you and Uhlenbeck have been very lucky to get your spinning electron published and talked about before Pauli heard of it. It appears that more than a year ago, Koenig believed in the spinning electron and worked out something. The first person he showed it to was Pauli. Pauli ridiculed the whole thing so much that the first person became also the last, and no one else heard anything of it, which all goes to show that the infallibility of the deity does not extend to his self-styled vicar on earth. And we talk about the Pauli theory of spin and teach it to our students. Yes. There's a certain irony here. So Fitz and Taylor at Illinois knew about spin, knew about all of this, and they did the Stern-Gerlach experiment with hydrogen, which was significantly more difficult. But they did see with no field and a broadening with, and basically confirmed that this magnetic moment of the electron was the same as Stern-Gerlach. It all began with Dirac. Dirac was trying to make a relativistic wave equation, and sorry? Oh, okay. A relativistic wave equation, and much to his surprise, he also explained the magnetic moment of the electron. Spin, the whole thing was built in. It's amazing. All you graduate students must go read Dirac's first paper. It's like reading a textbook, and it's absolutely brilliant. And if you do the non-relativistic reduction of the Dirac equation in a weak magnetic field, you find that L is equal to 1, G sub L is 1, and G sub S is 2. The next big development was Schwinger's calculation of the first radiative correction. So I'll have to talk about that for a minute and explain what a radiative correction is. But this is Schwinger's memorial stone in the cemetery where he's buried. And this opened up the field of radiative corrections in quantum electrodynamics. So, and it goes beyond just alpha over 2 pi, because there are higher orders, the perturbation expansion, and there are higher orders. So virtual particles increase the muon magnetic anomaly. This is the Schwinger term. And so the arm-waving argument, you've got the uncertainty principle, delta E delta T, so you can violate energy conservation briefly and have these virtual particles appear. And the energy you've got available is roughly the particle's mass, right? And so the electron's mass is very small. It's about, the muon's about 200 times heavier, so you might expect that heavier things would contribute more to the muon than the electron. And this is very important. And for example, the Z boson contribution is essentially negligible even at the parts per trillion that A electron is measured, but it's significant for the muon G minus 2 because of this fact. You get a factor of basically m mu over me squared contribution of heavier physics to the muon. So the muon provides a great laboratory to study physics beyond the standard model and physics beyond. And of course, QED is an industry now, and the 10th order contribution, 5 loops, 12,700 and some Feynman diagrams, lots of supercomputer time to evaluate all those integrals. And so when Gabriel's first published his electron G minus 2 that was so precise with the pinning trap, he made a comment that this was well beyond what anybody expected when they invented QED. And so he got a quote from Freeman Dyson, and so I thought I should get my own quote from Freeman. And he said the main point was that all of us who put QED together, including especially Feynman, considered a jerry-built and provisional structure which would either collapse or be replaced by something more permanent within a few years. So I find it amazing it's lasted for 50 years and still agrees with experiments to 12 significant figures. It seems that nature's telling us something. Perhaps she's telling us she loves sloppiness. So QED is amazing, and I'll come back to this later. So in order to calculate the standard model value of the muon anomaly, you need to know all of the standard model contributions. So, sorry, I'm feeding back. And so there's the electromagnetic, which now goes to thousands of terms. There is virtual hadrons. The strong interaction contributes. And there's a next order strong interaction contribution as well. But I've shown you the relative sizes of these, so QED dominates. Which is, if you want to be sensitive to all this stuff, you have to make a more precise measurement. And furthermore, there could be unknown particles X and Y that could contribute in loops. So let me just show you the experimental value from Brookhaven. This is 63 of these units, which is 0.54 parts per million precision. And this is the standard model value recently published in PhysRevD this year, or last year. And the difference is about 3 to 4.5 sigma, depending on whose theory evaluation you use, which is fairly interesting. And we're not looking for a bump. We're measuring frequencies, which I will explain. So here is a bunch of recent theory calculations. Since 2003, the strong interaction contribution has been pretty steady. It's just increased in precision. And so here's our B&L limits, and here is what Fermilab we expect to do. And so if things don't move, you could go well over 7 standard deviations. And that was sort of drove the design of the experiment. This shows both the CERN measurements and our measurements, and showing they're quite consistent, in fact. And anytime you have a deviation from the standard model, the theorists go wild. And so they've had a decade or so to go wild over our results. And so last I checked, there's over 4,000 citations to our papers. So there is some interest out there. So how do you measure the magnetic moments? And I just show our two, our present precision and our projected precision. And so Robbie, who also said, who ordered that when the muon was discovered, said, never measure anything but frequency. And that's because you can measure frequencies very, very precisely. And so how do you measure the frequency? Well, we have to use the miracle of parity violation. So for those of you that are not sure what parity violation means, if I look in the mirror, I see a man holding up his left hand. It's very disconcerting, in fact, to see a video of yourself where it's the proper hand, because it doesn't get reflected. And so parity is basically this mirror reflection symmetry, which turns out to be violated in the weak interaction, meaning there's a preferred direction in space. So here's a pion decaying to a muon, and we now know, because of parity violation, this neutrino is left-handed. It's spinning this way. And there's no right-handed neutrino, although people are searching for such a thing. That would be beyond the standard theory. And so that means that the muon has a definite spin, because you have to conserve angular momentum. And therefore, the muons are produced polarized. The weak decay, here's where the two neutrinos are going back to back, and the positron is going in the other direction. And so these guys are zero total angular momentum. So the spin of the muon is carried by this positron, information on that, which gives you a handle to know where the spin was when the muon was born and where it was when it decayed, which is what you want to know if you want to know how far something precesses. And maybe I won't go into detail on those. So the first experiment at Columbia Nevis that that measured parity violation, and there was also a University of Chicago experiment, but this is the one that did a counting experiment. So they brought a mixed beam from their cyclotron of pions and muons into this degrader where the pions were stopped and the muons have a slightly longer range. And so then the muons stopped in this carbon target, and then they looked for the decay, and with just two simple counters here. So this is an experiment that was probably put up in 3 days when they decided it was interesting to do. And what you wanted to look for is the angular distribution, because that's, if it were not uniform, it would be the sign of parity violation. And so they've got one counter. How do you measure an angular distribution with one counter? Well, what they did was surround their target in a magnetic field, take a narrow time slice, and then change the magnetic field. So then they're sampling the complete angles, and by golly, this is what they got. Clearly see parity violation. And they measured the G factor and found it to be 2. Now this was very curious. Here's this strange particle, and it appears to be like a Dirac fermion. They didn't give up, and you'll discover later on why this is the hardest way to do this experiment. And they found that, in fact, they had the alpha over 2 pi as well. And this said that the muon was just like an electron in a magnetic field, which is remarkable. And it, along with the discovery of the muon neutrino a few years later, actually really pointed to this generation structure of the Standard Model. So I want to talk about spin motion of magnetic field, because if you're going to measure, you need to know what the equations are. So the cyclotron frequency, if you have a uniform magnetic field, the cyclotron frequency is given by that. The spin rotation formula is given by this, where this is the Thomas precession term. And the spin turns relative to the momentum with this difference frequency, which is directly proportional to the anomaly. So you get 3 orders of magnitude sensitivity by measuring the difference frequency, and that's why I say the Nevis experiment was so damn hard. Because they had to do 3 decimal places just to see this Schwinger term. And so the thing that was invented at CERN was that you used a uniform magnetic field and an electric quadrupole field to focus the muons. Why? Because you need to know the magnetic field experienced by the ensemble of muons. And if you have multipoles in your magnetic field and moments of your muon distribution, they couple. And you need to know exquisitely both the multipole distribution, the magnetic field distribution, and the muon distribution. And so this trick of using electric quadrupoles actually made it much easier. So here's the full spin equations. And you notice the cyclotron frequency has this motional magnetic field term. To a relativistic particle, a magnetic field looks like a combination of magnetic and electric fields. It's just special relativity. So you get this motional electric field, and this is the full spin equation that Thomas published a long time ago, but written in modern notation. And if you take the difference frequency, you discover that there's this term. So that says that if the trajectory is not perpendicular to the magnetic field, and in the spinning trap, you've got this kind of motion, which we call the pitching motion. It changes the frequency, so you have to take that into account. And this motional magnetic field, if you have a non-relative, here's a parallel plate capacitor, non-relativistic particle that goes through there, this charge is going to fall. It's like a gravitational field. If it's ultra-relativistic, the spin will get ahead of the momentum. And so you might guess there's one magic value of gamma that the spin follows the momentum. And that's called the magic gamma, and that's when this term cancels. So we measure both the spin precession frequency of the muons and the magnetic field, and then we calibrate the magnetic field to the Larmor precession of a free proton. And so we do these experiments blinded, so we don't know the clock frequency. At Fermilab, it's plus or minus 30 ppm. So there's no way you're going to get an answer. And we have independent teams blindly analyzing, and I'll talk more about that. We had a relative unblinding of one set of analysis, which I'll show you. Okay, so this weak focusing, in accelerator physics, we would call this a weak focusing betatron. In fact, it's a uniform dipole field vertically, and this quadrupole field that provides the vertical focusing, because otherwise, without some kind of focusing, you get a helix. And so for positive muons, you've got this top plates plus. And there's the beam coming out at you from this picture, because I know the direction of the ring. So here's the pinning trap sitting at Brookhaven. It's about 15 meters total diameter. It's excited by superconducting coils. And this is what we had to move to Fermilab. Here's what you're looking at. It's a cutaway. Notice there's no gaps between the steel. The largest gaps were 20 thousandths of an inch, whatever it is in microns. Okay. And it's a C magnet because you've got to put detectors here. And if it's a C magnet, the flux return on this side is different from that side, so you get an inherent quadrupole that you have to get rid of, and I'll tell you how later. And this is compared with Gabriel's penning trap at Harvard, which is a few centimeters across. So the experimental technique in a nutshell, you start out with a narrow bunch of protons, you hit a target, lots of junk comes out, you select pions that will give you the muons you want, then they decay to muons, you bring it through a magic magnet I won't talk about that brings it into the storage ring, and in a uniform field, you come back and hit where you started. So you've got to provide some kind of kicker to put this on orbit, and then you need these quadrupoles for focusing. So that's basically this experiment in a nutshell. And you then put 24 calorimeters around to measure the decay products and give you this muon frequency. And you measure the frequency omega A. So the muon lifetime is 64.4 microseconds since this magic gamma. The period is 4.5 microseconds. And the cyclotron period is 149 nanoseconds around. So we do a blind analysis. I need to talk about this for a minute because if you know the answer when you start analyzing the data, or you know what you'd like to get, you can bias the decisions you make. So how do we remove this bias? Our absolute clock frequency at Fermilab is blinded to 30 ppm. Since we're measuring a fraction of that, we don't know anything, which is really liberating to be free. We have independent teams analyzing the magnetic field. And there are two major analyses, actually three. We have 6 independent people analyzing our run 1 muon frequencies. Initially, they're blind to each other. Once you think it's mature, you then unblind relatively and see if you agree with your friends. If you don't, somebody made a mistake, and you don't know who made a mistake, and you have to figure it out. If they do agree, you say, oh good, we can go on to the next data set. Only when everything is complete do we get the true clock frequency, and the people from outside from these people outside the collaboration that have it. And using the word of kaon physics, where you had a box in phase space you didn't look in, we open the box. And of course, there was a famous box to put all bad things on women, I guess, is what I read, that out came all kinds of bad stuff from Pandora's box. But it's a surprise. So let me just show you, this was installing a pole piece in the magnet. Can you close those blinds so we don't get so much light on the screen here? Or is that not a blind that closes? Sorry.
Yes, problem with the light for the camera.
Yeah. Keep closing. All the way. Yeah, you can see better now, right?
She needs some lights, she said.
Okay, well, okay, this is much better, right? You can actually see that this pole piece, which is several tons, is suspended on this special fixture, and there's kapton on the ends. Why? Because if you have a quench, you don't want eddy currents running all the way around the magnet, you want to localize them. And here shows where the calorimeters go into this notch in the vacuum chamber, so there's very little material. Well, here it was, starting to take it apart. You can see the steel came out. It came in on a truck and can go out on a truck. However, these coils were built in this room. So what do you do with them? Well, you build a 40-ton fixture to hold them. You get it outside the building. There it is. And here it's nude. Then they shrink wrapped it. And it had to be moved along the roadways. Here it is coming down the William Floyd Parkway on the way to Smith Point Marina. And of course, you have to close the roads. And to tell you a brief story about Brookhaven Lab, the locals are very suspicious of the lab. There's always something they think is going on. And so amongst the things that they think is that an alien spacecraft crashed somewhere on Long Island, and some people will show you where. And it's at the lab, and some people even believe there's an alien at the lab. And you think I'm joking, but I've had a number of people, when I've told this story, says, oh yeah, I was riding the limo out from LaGuardia Airport, and the driver told me about the spaceship. So it's true. So anyway, there was a viewing area, and there was this guy there, local, that saw this coming down the road, and he says, that's a spaceship. And he went on and on with the rant. This is a cover-up, you know. So it was, and I wouldn't believe this except that summer intern caught it on his iPhone. It was hilarious. So there it is coming down the road. Here it is with the big moon. Here it is being craned onto the barge. Here it is on the barge, an innocent bystander. Here it is going by the arch in St. Louis up the Mississippi. Oh, you can barely see this. Okay, so we started out in Long Island. We had to port for 5 days because the seas were rough here. Then it went all the way around Florida. The Mississippi was flooding, so it went up the Tom Bigby Waterway and eventually joined the Mississippi and eventually ended up on the shore in at Lamont. And then we had to close roads for 3 nights, including 2 interstates. I'm sure the drivers were not happy at 2 in the morning. And here it is at Fermilab. So you can put it back together again. And so at Fermilab, we can make more or less the dream, the beam of our dreams. It's not perfect. One would prefer more than the HF booster for making the pions, but okay, you can't have everything. So we take 10 to the 12th protons out of the machine. We then rebunch them to 4 bunches, so you lower the instantaneous rate. And so they get stored in this recycler ring. We peel one off. We hit a production target, which is the old antiproton target. Then we go into what's called the delivery ring, which is the repurposed debuncher ring. And all the pions go away. At Brookhaven, we had a 75-meter beam line, and there were lots of pions, and that was a background problem. Then you put them in the storage ring and you measure G-2, what could be easier. I just want to particularly acknowledge in Italy the contribution from our Italian colleagues, particularly on the laser system. And Carlo Ferrari back there can tell you more details, right? And so we have tracking chambers inside the vacuum. And so when a muon decays, it can go through these tracking chambers and you see a track. A lower momentum one has a shorter time of flight because it curves. The radius is smaller if it's lower momentum. And so here shows these tracking chambers, and you can see a trajectory very nicely there. They're only about this high, and they have to have, all the electronics are here. The gas comes in through these manifolds and so forth. And so from here on is in vacuum, as you can see. And the beam is going into the board here. And of course, depending on the momentum of the decay positron, you can see further back in the storage ring. And one of the first things that was done is to look at the momentum in the tracker and the energy in the calorimeter And these are positrons, where the energy and momentum are basically equal. And this little bit is muons lost from the storage region, because there's almost no energy deposit in the calorimeters. And you can reconstruct the beam distribution. You say, oh my goodness, it's supposed to be a nice circle in the center. And that's because our kicker magnet has not reached its design field. And by the way, this kicker magnet has to turn on, kick the beam, go away, and not leave a field behind more than 1/10 of a ppm, and that has to die out quickly. So it's not a simple particle kicker. And if you do the projection, you say, oh dear. Nevertheless, and we have to make a correction for this E field, but it turns out that it's not nearly as bad as we initially thought. So, this is a plot showing if you set a single energy threshold and as the spin is turned around, you get more and less high energy positrons. Remember, they're correlated with the muon spin. And so this is exactly what you see. This sinusoidal oscillation as the spin turns around. And if you just take the tracker and make a momentum cut, this is exactly what you see. This is the G-2 precession. And that's pretty amazing. But the calorimeters, who have much better timing. This is our so-called 60-hour data set, and I'm allowed to show this, which has about 1.2 parts per million sensitivity in 60 hours, which is good. And it's folded back on itself, because if I made it straight, it would go way across the room. So, but you can see there's no, well, maybe there is a fit function, but basically you would agree that it looks like cosine omega t plus phi with the muon dilated lifetime. However, so we got many wiggles per muon lifetime. And the sensitivity goes as 1 over the square root of n. However, there's a 2 because these are completely correlated. The phase and the frequency. Here's a Fourier transform of the residuals to that 5-parameter fit, and you see lots of things from beam dynamics. And I'm not going to talk about beam dynamics unless I get a question, but the beam is like a beam in an accelerator, and so you have to understand that and correct for it. And this coherent beam oscillation is beam, when it's bunched, moving back and forth, seen by a detector. And you can see that the fit isn't very good because there's still some omega A in there. So the fitting I could give you an hour seminar on fitting, which I won't. So here were the 60-hour data set. Everybody's blinded to each other. Here is relatively unblinded. And we all heaved a great sigh of relief. This was done in real time. And we all said, oh, good, on to the next data set. So let me tell you in my waning moments about the magnetic field, which is amazing. You see, we have a tube like this, where we've got the muons stored, and we need the field, we need to know the field to sub-ppm level, and we need to have it as uniform as possible, and this is a 44-meter long tube. It's only 0.3 of a cubic meter, but if you think of a 44-meter long tube, that sounds a bit harder. So we have these 12 yolks, and there are these top hats which you can adjust the effective mu of the magnet by moving them up and down. Of course, they're big pieces of steel. There are the poles, which we moved up and down and shifted around and stuff to micron level. And, well, you can't see this too well, but these are the pole pieces sitting on the ground before being installed. there are these wedges that can both move in and out, which changes the dipole. And the angle of the wedge shims out the quadrupole. There are these edge shims, which basically shim the sextupole. There are 8,000 little pieces of iron, which I'll show you a little later, stripes, custom put on G10 and then glued to the pole piece. And there are surface coils with 2.5 millimeter spacing that go all the way around that we can power individually to shim higher multipoles and also to correct if there's a net radial magnetic field, it raises the beam, and so we can recenter the beam with that. It's a major, major thing. And when we're running, we have 378 probes embedded in the outside of the vacuum chamber that monitors the field while we're running. And every once in a while we stop the beam and we run this little trolley which has an array of probes which are clearly designed to do multipole decomposition that measures many, many, many points. And it's just a standard NMR probe. We're using petroleum jelly because it doesn't evaporate like water, which we tried at Brookhaven, and we learned that the probes were dying. And it's perfectly stable. It was studied by one of our postdocs very carefully. This just shows a free induction decay, which very good signal to noise. So in a single shot, you get a 30 ppb measurement. So this is precision NMR magnetometry. Let me just show you when we first turned on the magnet. This is a shimming trolley with a whole bunch of probes that goes out to much larger radius. And you can see these gradients are just telling you that there's lots of, these beating tells you there's lots of gradients in the field, which you knew when you turned it on. You get 10 to the minus 4 if you're lucky with a good magnet. So I have to, let's see. Oh dear. There we go. So this shows shimming the field over time. Started in September, October of 15. And first they moved the top hats. First they did the pole pieces. Then they did the top hats. Then they adjusted the wedges. And the blue is Brookhaven. And you keep going, and you keep tweaking, and you keep doing things. And at first we were calibrating, if you move something so many millimeters, how does it change? That was why there were these wild variations. And here's where we ended up. This is 100 ppm over 44 meters. And this is azimuth, okay. And here are the little stripes of iron on G10, each one custom cut and weighed and whatever. And so here is the field averaged over azimuth. And why can we say the average, azimuthal average is the important thing? Because the beam slowly moves up and down and in and out. And so it samples the whole magnetic field. So it's this azimuthal average that counts. Here's the dipole moment, and this is 100 ppm. The RMS is 15 to 20 ppm over 44 meters. And we run the trolley at different times of the day just to make sure there's no stomatics. The fixed probes monitor it, and we've studied how the fixed probes track the real field with the trolley. And we eventually cross-calibrate each of the trolley probes to an absolute calibration probe. So there's a huge amount of magnetic field technology. And we normalize to the magnetic field to the Larmor frequency of a free proton averaged over the muon distribution. And so this is what we measure, and these all come from the literature. And that's what gives us the anomaly. With this systematic error budget of 70 ppb, on both the muon frequency and the magnetic field. Here's an aside that's recently come available. The quantum electrodynamics contributions depend on alpha, the fine structure constant. Remember, alpha over 2 pi was the lowest order, and so the next order is alpha squared and alpha cubed and so forth. And a new measurement of alpha, independent of the electron G minus 2, has come up with a value that's different from what the electron G minus 2 gives you. So here's the alpha from from the University of California, Berkeley, and here is what you get if you use the electron G minus 2 to determine alpha. And so there's a difference, a small difference. And so Gabriel's is planning a new experiment 10 times more precise for the electron to see. And the other amusing thing about this is that this is the opposite sign of the muon deviation. So maybe there's something there, maybe it's not. 2.4 standard deviations, okay, whatever. Okay, so let me conclude. So the muon magnetic anomaly has an independent role, an important role in the development of the standard model. And I think I've persuaded you of that. In the generation structure of the model, the first 2-loop electroweak calculation, which turned out to be really hard, the necessity of including all of the standard model forces, including the electroweak. And in fact, the 2-loop electroweak calculation lowered the electroweak total contribution by about 25%, 20%. There's a possible difference with the standard model, which is sort of the holy grail of particle physics today. And the interesting thing is the measured value of the muon anomaly is a sum over all physics, known and unknown. The question is, for this new physics, what's the mass and what's the coupling to the muon? And we've got this new experiment online. It's, we've got about 1.4 Brookhaven with this constant conditions this time in run 2. We look forward to analyzing that, where it's much simpler than run 1, where there was no time when everything worked for a long stable period in run 1. So, if this new result from run 1 agrees with the B&L result, we could easily go over 5 standard deviations. We'll see. Or we could come close to the standard model, who knows? But if it's a statistical fluctuation of this distance, we really made a mistake. And we keep asking ourselves, those of us from the old experiment, did we up? And we haven't found anything. We found effects, and then we've gone and, oh, it's not important. So I just wanted to end with this picture of the collaboration standing on the magnet at Brookhaven, which would never be allowed by the safety people today. In fact, there's no guardrail, there's no anything. We're not on, harnesses from the ceiling. And in looking at this picture, I realized how many dead people there are there. So Frank Krienan, who was a chief engineer at CERN and worked on the G-2 experiment there, and then came and worked on our experiment. Francis Farley, who did all of the CERN G-2 experiments in our first experiment, he died at 90-something last year. Vernon Hughes, who started the Brookhaven experiment, didn't live to see the final result. And Gordon Danby, I don't know how he didn't get in this picture because he designed the magnet. It was his magnetic design with all these shimming tools built in that made it work. So the question is it going to be inside or outside of the standard model?
Thanks a lot for the very nice talk. Are there questions?
I have two. So one, the first one is the following. So I saw that the LHC measured the light-by-light scattering, which is giving, I think Atlas has some events where two photons are, one photon is emitted by one proton, another photon is emitted by the other proton, and they scatter. Yeah. So the question is whether this knowledge can help, no? Making the prediction more accurate, given that it's one of the contributions.
Okay, so that's a good question. And the LHC is a difficult place to try to study that. There are data from previous electron facilities that actually do gamma star gamma or gamma star scattering. And that's important. If I can go back to my slides here. Well, first I have to find the mouse. Okay, so the question is, how do I get back to my home screen? Not that way, not that way. Ah, great, here we go. So the light by light is relevant for this diagram. That's, oh, there it is, thank you. So this diagram is 2 photons in, 2 photons out, if you want to look at it that way. It's called, that's why it's called light by light. And this is a hadronic bubble. And so at electron machines, there are data on, and it's dominated by the pi0 pole, which is, you know, I don't think I have that picture. Anyway, the pi0 pole, instead of this blob, you put a pi0 pole in there, and there's 2 gammas on one end, and there's 2 gammas on the other. And so with existing data, in fact, Colangelo and other collaborators have calculated using dispersion relations instead of models the pi0 pole using gamma star gamma to pi0. And what they found was that they agreed absolutely right on top of the model predictions, which have been used before to estimate the light by light. And of course, you get much higher intensity in an electron machine than you do in LHC. There is a program of 2-photon physics at BESS, which is an electron machine in Beijing, that is taking data now to add to this dispersion approach of determining the light by light. And of course, it's the pseudoscalar poles, the pi0, the eta, and the eta prime that are important, but the pi0 is the dominant one.
Okay, thanks. So, and then the second one is, you mentioned that there is another experiment in the very last slides, that there is another experiment which measured the fine structure constant. Which kind of experiment?
It was published in Science in 2018. It's a University of California, Berkeley, Holger Müller?
Which kind of, so it's not a G-2?
No, it's cesium atoms, dropping them, you know, with incredible, it's an incredibly complicated experiment because it's so precise.
Are there other questions?
I was curious. When you displayed the blinded results, there was one group with significantly higher uncertainty with respect to the others. It's because of different systematics estimates?
You're very observant. The one with the higher, all of the analyses except for that one use individual events and then sort them in a certain way and fit them in different ways. Okay. which we call the so-called T method, because you've got everything as a function of time, and then you do a fit to that. The Q method is sort of in the spirit of the very high intensity parity violating electron scattering experiments where they just integrate. And so in the Q method, you basically take all the events and you get a little less statistical significance, but in principle, more statistics. However, because of computing limitations for the playback, because we have lots and lots of data, we don't have as big a data set there. So it's just a smaller data set. And of course, all of those different analyses that I showed you that agreed have very common data sets, but some of them are quite different in their approach and they're sensitive to different effects. And we're thinking about how to put them together. I mean, one choice is they all agree, take this one. But we have Alex Kajravasi, who was the K of that K and T theory evaluation, who had to put together all of these disparate sets of E plus E minus data to determine the hadronic contribution, is now in our collaboration as a postdoc. He switched to experiment. Job prospects are better. And so he's thinking about how to put all these correlated data sets together. So we might do it, I guess, right, if you'd call that right.
A funny question. Can you observe a CP violation in your experiment?
No. Well, I mean, at Brookhaven, we did mu plus and mu minus, and so we looked for CPT. And of course, we didn't find it, or you would have heard about it. But, and there are these models by Alan Kostelecki and collaborators about Lorentz and CPT violation, looking for diurnal variations and so forth. And we also did that analysis at Brookhaven. We didn't find anything. But that model's got so many different parameters, even if you, it's a very complicated model. But
okay. Thanks a lot. Let's thank the speaker again.